There we go. Welcome to EM360 Live, a monthly live Q&A where we pick the brains of some of the most influential people shaking up the enterprise tech space today. My name is Matt Harris, Head of Content here at EM360, and today I'm joined by Dr. Jim Webber. Jim is a visiting professor at Newcastle University, as well as Chief Scientist at Neo4j. And we're here to talk about knowledge graphs and why the future is a knowledge lake. Welcome, Jim.
Hello, Matt. Thanks for hosting me.
Yeah, no worries at all, Matt. How are you doing today?
Yeah, I'm doing very well indeed. Lovely, kind of warm end of summer here.
Yeah.
Going to do some excellent tech nerdery in the next 20 minutes or so. What's not to like?
Exactly that. Jim, for those who don't already know about you, do you want to just kind of run through a little bit about who you are and what you do?
Yeah, for sure. So, hi, folks. My name is Jim Webber. I'm Chief Scientist at Neo4j, and I have as Matt mentioned, I have a visiting professor role up at Newcastle University. And what I do is I work on research for the Neo4j graph database and associated tooling. So I'm on the kind of research end of the spectrum. So I think about things that might yet come, as opposed to my colleagues on the product spectrum who ship the software that some of you might use every day.
And obviously you've done, some super interesting kind of commentary on knowledge graphs and kind of, the kind of space they take up in the industry at the moment. Could you just explain to those who may not know what knowledge graphs actually are and
Sure,
why they
absolutely.
should be, and also, why they should be an important consideration to everyone from, developers to data scientists, IT managers, and even the C-level as well?
For sure. So let me start with what a graph is, because I think that's an important foundation before we go on to the higher level patterns. So some of us that did computer science at university have been scarred by graphs, right? We had the kind of leather elbow patch professor teaching us with a chalkboard about all of these graph algorithms with kind of fancy Dutch names and so on. And that's kind of a scarring experience. I think in a lot of higher education, graphs are presented as this kind of austere mathematical thing. And we learn how to do algorithms on them, like we learn how to do graph searches. We learn how to do things like minimum spanning trees and all these kind of things. And I think they sound very computerish and algorithmic. And actually, in the modern world, graph databases or graph data aren't like that at all. They are these wonderful, rich data models, much like relational has a wonderful rich data model. But instead of the data being stored in tables, which we then do the kind of join operations and have foreign key constraints and all that stuff. In a graph world, we have entities, which we typically call nodes. We think of them as round for historical reasons. And we can connect those entities together in any way that we like, using things that we call relationships or edges, if you're mathematically inclined. And if you take these nodes, the entities, and these relationships, you can start to create a graph or network structure that represents your domain. And it's high fidelity. It's a knowledge graph because it contains information, not just structure as the mathematicians like. But those of us in the data world, we like rich knowledge. They become knowledge graphs because those entities, those nodes, have labels on them that tell you what their function is in the network. Is it a customer or a product or a road junction? And they have data in them. Right? They have property data that gives you the actual data about the entity. And the relationships that go between them, they're directed. So you can say Jim follows Matt, which implies that Matt has Jim as a follower, because you can read them in either direction. And they're labeled. They always have a type on them. So it's a follows or likes or bought kind of relationship. And you can also have properties on those relationships. So you could say that the distance between two road junctions is 250 meters, or I bought this product in 2017. And when you bring these very simple idioms together, you can create very rich data models, which today we know as a knowledge graph, a very information-rich data structure, which we can query like a traditional database, albeit typically much faster, and we can process using some of these graph algorithms that we were scarred by at university to gain insight out of the whole graph at scale, to find things like popular users in a social network or single points of failure in an IT network and so on. So actually a very simple idiom, and it's what drew me back to databases after several years where I was off working on other things. This model kind of blew my mind about how simple and useful it is. So I've spent the last 13, 14 years working exclusively in this world.
Have you got a particular favorite knowledge graph or a particular, favorite application, or is it a bit too much like choosing a favorite child?
That's a tyrannical question to ask, because it's grown over the years. If we were having this conversation way back in like 2010, when I first came onto the Neo4j payroll after being an open source contributor for a while, it's a really easy question to answer. And I'd say, oh, if you're in telco, you should do knowledge graphs because you're already familiar with graphs or networks from your domain, right? In fact, the first time I used Neo4j in anger was in telco. Or I'd say, oh, if you need to add social features to your system, that's obviously a graph problem because Twitter and Facebook had popularized the term social graph. So it's very easy in. But over the years, I've been and continue to be delighted and astonished when users tell me, oh, yeah, I built this system. It's a graph. And I have to sort of think for a moment and think, well, is that a graph? So someone, if you've ever stayed at a Marriott hotel or one of the Marriott group hotels, the price you paid for that hotel room was a graph. And I went, wait, what? How is that a graph? Sort of scratch my head. I could understand how Twitter is a graph, and I could understand how the London Tube network is a graph. I can even understand that the rail network that's let you down today is a graph. But a pricing engine? And then someone explained to me, well, look, traditionally, a pricing engine would be a spreadsheet, and a spreadsheet is a graph, right? All those connections and dependencies between cells in a spreadsheet, that's a graph structure. So why wouldn't you take it out of the spreadsheet, formalize it in a graph, and now you've got a pricing engine where you can not only do arithmetical things, but you can also mix in social things. Hey, there's a big ball game near your hotel tomorrow, or there's a rail strike tomorrow, so people are going to need to stay, locked away in London, for example, rather than returning to their commuter towns. So you're able to factor all of those things into a knowledge graph, which makes it much richer than those kind of graph models that the mathematicians so love. But if I had to pick a favorite, and this is still in my heart because it was the first system I worked on in anger, it would be recommendations. So the ability to understand people, because graphs are great for people. There's a huge amount of research and practice in studying people-centric graphs or social graphs and how they behave with respect to buying habits and stimuluses and so on. So the first system I ever worked on was all about making sure that you as a customer got good recommendations. So I was working for a telecoms company, and it was some years ago. So we had a call center, and the idea is that, Matt, you'd phone into the call center and we'd have a lovely chat and I'd solve your problems or whatever. But I'd also know what products that you bought from us. And based on those products, I could see other products that would depend on the things you already owned. And then I was able to traverse those dependencies in the graph and perhaps recommend them to you. So perhaps I see that you've got digital phone installed at home. Now, I know that digital phone requires a digital modem to be installed in your home, and other products that depend on that digital modem would be basic internet and video on demand. So immediately I can make good recommendations to you, which wouldn't conflict with anything you've currently bought, that would fit within the portfolio of products that you might want. And once you've got basic internet, I can see that premium internet depends on basic internet, it depends on digital modem, so I can offer you good choices. Now, if you compare that to the way, for example, even big companies like Amazon work, they're terrible. I'm a middle-aged bloke, so I buy shoes very infrequently. Right, that's what we do as middle-aged blokes, isn't it? You've got your gym shoes, you've got your posh shoes, and you've got your daytime shoes, and that's pretty much all the shoes any middle-aged bloke needs. But I bought the shoes off Amazon. I know it keeps telling me, "Hey, buy shoes. Do you want some shoes? Do you fancy some more shoes, Jim?" I'm not an octopus. I'm a biped. I only have a limited number of feet that I can put these shoes on. So their model hasn't taken into account the dependencies and the kind of social complexity of being a middle-aged bloke and only needing one pair of shoes. I mean, it'd be like trying to sell me multiple toilet seats, which was a viral meme on Twitter not so long ago, where Amazon was bombarding a user with adverts for toilet seats because they'd bought a toilet seat. So I think that one was my favorite, but from there it exploded. And now we see knowledge graphs being used in applications from HR and skills management over here to managing power grids over there to helping TfL move Londoners around the city on a daily basis, in banking to look for fraudsters and make sure that people aren't breaking the rules and so on. And this whole universe has exploded. And I think I'm bold enough to say now, having experienced it for over a decade, that knowledge graphs and graphs generally are becoming a kind of good general purpose underlay for most systems that deal with complicated real world data.
I was going to say as well, like obviously, you've got huge amounts of data going into these things. You're going to probably need some form of AI to kind of power that kind of integration. How is AI really being integrated into these kind of pattern detection knowledge graphs?
Yeah.
And how does it work with natural language as well?
For sure. So look, AI is everywhere in our
Of course.
enterprise IT nowadays. From a few years ago, where it was like a curious plaything, it's just mainstream, right? So we get a lot of benefit from both being AI in the box and cooperating with other AI systems in the ecosystem. So inside the knowledge graph itself, inside Neo4j, the products I work on, we have this idea of graph native learning. So if I have a graph structure, nodes and relationships with connections and labels and all that nice stuff, you can actually ask the data itself, hey, can you evolve? Could you maybe suggest missing links, missing relationships in the database? So we have our internal graph native engine that will say, hey, I think there should be a link between these two people. I think it should be labeled friend, that kind of thing. So it will try and complete a graph which is incomplete. It can also predict labels of nodes, so predict their roles based on their structure in the network, and even predict missing properties now. Oh, I think given the structure of this network, I think this node that's a person is missing an age, and the age should be 29, that kind of thing. So we've got AI going on to kind of enrich the data. But we've also got it going on in kind of traditional machine learning pipelines. It's funny to say traditional, right, for a practice that's still relatively young, but folks out there, folks listening on the live stream or on the recording will definitely have ML pipelines in their org. And the way that they'll work is they'll go to their database, typically a relational database today, and they will mine columns from it. They'll mine, age, gender, postcode, blah, blah, blah. And then they will use those features to train a model, and that model will then be put in production if it's good, and it will be used to answer some queries or predict some queries. So you create a curve that will be able to answer some queries. That's great, but what a graph has that those things don't is topology. So you can actually start to take the topology of the graph. You take the page rank of a node. You can take the degree of a node. You can take the community of a node. You can take the centrality of a node, how popular it is, how much influence it has, and encode all of those as features as well, so that you have more features for your machine learning model. And what the data science community tells us is that within reason, more features is better. And in fact, now you can even take the topology of the graph itself and encode that as a number, as a vector, so that you can, through node embedding, so you can just encode the topology itself and use that as a feature, which gives you a super rich set of ML features to train your model on, which typically gives you a better performing model.
Oh, Jimmy, you still with us?